we're good to go with my fuzzy document can. All right, so any questions up to here? It is right side up. I wrote some code, man. It happens once in a while. Yeah, it's interesting over break because you stop using something for a few weeks and you come back and like things have changed, and Zoom is like that, and my camera setup was like that, so we'll get it dialed in. Alright, there's something I'm not doing. I don't know what it is. Well, it's pretty easy to go like sideways. And I can actually do all kinds of effects. That's always fun, having people look at your house for, I'm guessing you're selling. That can be challenging. Yeah, I can do weird things like that. Like a square root lens. I can go X-ray mode. All right. Any questions so far? If not, let's start by talking about the ODP. So ODP 213. I know what I forgot. I have to put these on canvas. I will put them on canvas after class, but anyway, you have ODPs in the works again. So 213 is due tomorrow, so we're playing with hash functions for the next 2 assignments. Alright, so here's the deal. Make a function called hash. Okay, simple prototype takes in a string pointer, returns an integer. This is the hash function that we've been talking about, where you basically just add up ASCII codes of characters, and in this case we're going to reduce mod 31. So your hash function is, you know, sum Right, that's how you hash a string. So add up all the characters, first character through the last character, reduce mod 31. Okay, how do you add a character? If you just add str bracket I to a running sum, it will take the ASCII code of that character, treat it as an integer, and add it. You don't have to do anything weird with converting or anything like that. And here's some examples. If your string consisted of a single letter, just A, right, that should hash to a value of 3. Why? Because the ASCII code of A is 65, 65 mod 31 is 3. If your string consists of 3 characters, A, B, C, or any other order of those, CAB, BAC, etc., some of the ASCII codes is 198, that should give you a hash value of 12. So there's specific examples here you can use to test. Right, write a main program and just print out hash parentheses, double quote, hello, you should get a 0. Hello with uppercase H only, you should get a 4, and so on. So really easy to test with these test cases. 2 really important things to pay attention to. 1, Don't treat new lines or any other character any differently from, you know, a letter or a digit or a punctuation mark. Don't do anything fancy. Just add up the characters, reduce mod 31. 31's prime. It's my second favorite prime number this week, so that's the significance of it. There's reasons why it's nice to use a prime number for the size of your hash table. And so this is representing a hash table of size 31. We'll see some of that when we start developing some algorithms, but it's mostly a random number. So, all right. So don't treat any characters differently from any other characters. Don't you know, ignore punctuation. Don't change things to uppercase. Don't get rid of new lines. Nothing funny, right? Just add the ASCII codes, reduce mod 31. But you do want to be careful. 13 is a cool prime number. You do want to be careful if you're testing this and you're using fgets and you type in hello and try to hash, you're not going to get a 0, you're going to get a 10. Why is that? Because fgets is glomming a new line onto the end of your input. So if you use fgets and you type hello, enter, and you pass the string that you got back to hash, it'll look like your hash function isn't working. How do you deal with that? Don't deal with it by changing your hash function, right? Deal with it by understanding that if you type hello followed by a new line, you should be getting a hash value of 10 because the ASCII value of a new line is 10. And a hello lowercase, you would get a 14. And a helen, you would get a 30 plus 10 is 40, which will give you a 9. Right? So think about that, and don't take the advice of well-meaning friends or random strangers on the street who say, oh yeah, in your hash function you should just, you know, if it's a new line, just ignore it, don't add it, right? You do that, it's not going to work. All right, so write your hash function, test it, and then assess it with testbed ODP213.0, and you should be good to go. And then tomorrow's ODP, we're going to do the same thing, but we're going to add a second argument to the hash function, which will be our probe value. So not a big surprise there. All right, any questions about the ODP? Oh, especially if they work for Google, don't listen to people on the street. But if they work for Boston Dynamics, you could listen to them. Yeah, so there's the summation. So string length of string minus 1, that's the index of the last character. So if this is HELLO, this would go from 0 to 4, and just add up each of those. Yeah, you're welcome. What day are we? We are the 2nd, so this ODP is due the 3rd at 10 a.m. All right, your ODP is posted on Canvas. Is it Groundhog's Day? I'm still waiting for winter to start. I'm not really worried about it ending. I'm waiting for it to begin. But we had snow last week, so that was nice. On the other hand, my mom in New York, you know, she gets like, 30 inches overnight, which is like a pretty righteous winter. Let's see, question. So we should get rid of the new line that fgets puts in the string. That's totally up to you. If you're going to test your code by using fgets to type in a string, and you want your string's hash to give you the same values you're seeing here, then yes, definitely get rid of the new line before you call your hash function. If you don't want to do that, right, you can hash hello with a new line at the end, and you should get, a 10, a 14, an 11, and a 9. So either way. Or, you know, just test your function by saying, you know, something like that's totally legit. So this calls your hash function with that string, 5 characters, takes the integer and it'll print it out. And your program should say hash of hello equals, and it'll print the value that you got back from calling your hash function, which in this case should say, you know, hash of hello equals 0. So you could hardwire a set of tests since I gave you some specific values. If you want to play with it more generally, go ahead and use fgets and so on. So any of that will be fine. Cool, other questions? All right, I will call that good. All right, so let's start looking at some of the algorithms that we use for working with hash tables. And I think this is going to be your third assignment, by the way, is a hash table. I think I'm going to do a hash of some kind of structure, either stacks, queues, or lists, or maybe a hash of hashes. All right. So our hash table is basically an array. I'm going to call it H table. And it's going to have a set of entries, a key. Usually this is called key and value, but it's just a name. But you know, you would make some kind of structure. Let's think of it as a hash entry. And I don't know, let's just go with strings. All right, so there's what a hash entry looks like, and we're going to add some other stuff in here pretty soon. But our hash table would be struct hash entry. Would be an array of these entries. So I'm fixing the size, for example, 31. If our hash function always gives us numbers from 0 to 30, then 31's a good size. But we could, you know, do this as a star struct hash entry, and then we could malloc it or whatever. So I'm not going to worry about coding details yet. I want to look at algorithmic aspects of this, but I'm just kind of giving you a heads up on that. So we have a hash table. It's got a key and a value, and it looks like an array, so there's indices on each of these. And what do we want to do with a hash? What's the view from the perspective of an abstract data type? So we want to do some kind of initialization, always. We we want to be able to store a value associated with a key. This is usually called put. So put this key value pair into the hash. We want to be able to get a value associated with a key. So call a get function, have that return a value. We want to be able to remove a key. And maybe we want to do a search, or maybe our get function just tells us, whether or not it found a key. So we could have a special value that comes back, for example, null. But let's go ahead and put a search in because we'll develop code for that. So our main program would, call in an init to create an empty hash, store things using put, retrieve things using get, delete things using remove, search for things using search. There's one other thing that we need here. So if we have an array of data, like CSE222A style array, and we wanted to print out its contents, we could just make a for loop. For I equals 0 to 10, print array bracket I. For a linked list, if we want to print the contents, we start with the first node, we print its data, we follow the chain of links from node to node until we get to a null pointer. For a hash, it's a little trickier. Now, as an abstract data type, our main program does not know anything about this H table. It does not know anything about this struct hash entry. Those details are hidden underneath the firewall, right? The main program wants this unified interface to the hash. And we can implement a hash as an array, we can implement it as a linked list, we can implement it with a whiteboard and a cell phone, right? So the main program's interface should not include any aspects of that underlying array. So we would not want to print an array, for example, by saying for I equals 0 to 31, see if this entry is valid. And if it is, go ahead and print that, right? That's not what we want. So we need some kind of way from our user code, our main program, to go through the data that's in the hash. And so we've been calling this traversal for a linked list, traversing a linked list. We'll use that term for trees also. But hashes are kind of tricky. If you remember when we did associative arrays in 224, you built up this hash that had all the phrases in your text, and then you wanted to print them out. And you can't just print, for I equals 0 to 10. And if you don't know what the phrases are, you can't ask for how many times that phrase occur. So we introduced a notion that was called an iterator. And an iterator is something that lets you go through a data structure and it feeds you things from that structure one at a time. So let me just call it print for now. But we're going to want something more special than that. But for now, we'll just think of a print function that will print the contents of the hash in no particular order. All right, so how do we initialize? Well, we've got an array. If we're just going to allocate it statically, right, it's just going to be something like this. If we're going to do a struct hash entry star H table, then init would need to do a malloc based on how big we want the initial hash to be. But the main thing we need to do for init is we need to clear out these valid bits. Right, so arrays always have stuff in every entry. but we set the valid flag to 0 to say this is not part of the hash. There's nothing stored here. Alright, so init so allocate storage for array if needed, and then set all valid flags equal to 0. And that's pretty much it. Alright, so let's put something in our hash. This is where it gets fun. So you've got a key and a data pair you passed to your put function. Where do we want to store that data in this array H table? Hold on a second. Let me see access errors for the ODP. Let me take a peek. Interesting. Alright, ODP should be working. Yep, someone's assessing already. But no cookie. Alright, I'll figure out later why it wasn't working, but anyway, that should be up now. Alright, so let's do the put command. Alright, so where should we store this key data pair in the H table? What's an expression we could use to figure out where this gets stored? This was not a rhetorical question. So we were talking about hash functions yesterday. What's a hash function have to do with storing a key data pair? Key in the key part, data in the data part. Key part and data part of what? You're correct. The H table, okay, so where should we store these in the H table? Where our function tells us which function. the hash function. There we go. Okay, we've got a path to truth now. So yes, this is an array of structures. We're going to store the key data pair in one particular hash entry, right? One of the elements of this array. Which one? The one given to us by the hash function. So what do we feed to our hash function to get that index back? Feed the key. Okay, you got it now. All right, so index equals hash of key. All right. Take your key, run it through your hash function. You get back an integer, presumably between 0 and 31. We're assuming in this case between 0 and 30, right? So we're assuming there's 31 entries available in the hash table. So get your index back. That's just a plain old int that tells you where to store your key data pair. So normally you could do something like, you know, htable index dot key equals key, htable index dot data equals data. Okay, that's logically what we want to do, is copy the thing we're trying to put into our hash table into the key and data locations. I put question marks there because if these are strings, we can't just do an equals statement. We need to do a string copy. And if we actually declare our hash entry to look like this, we can't just use a string copy because we're going to segfault. Because I've said a hash entry contains a pointer to a key and a pointer to a value, but they don't point anywhere yet. We need to do a malloc first. So there's all kinds of legwork you got to do here now, right? If we want to actually copy a key data pair into our hash table, we need to set hash table index.key equal to malloc, and we need to allocate enough space for the key. So how many bytes do we need to store the key? Key is a string. How do we figure out how many bytes we need to ask malloc for? You didn't know I was going to make you work this morning, did you? String length, okay. String length of what? String length of the key. Almost perfect. We could do -1. So suppose my key is hello, HELLO. And I'm going to try to copy that string into some location in memory, and I'm going to set this to point to a block of memory where I can store that string. I actually need to do +1 because I need to store HELLO, that's the 5 letters, and I need to store the null terminator. If there's a new line at the end, that'll get counted by the string length. So that would automatically add an extra 1. But we need to explicitly set aside space for the null terminator. Otherwise, when we come back and we try to look at this key, we don't know how long that string is. So that's tricky, right? That's going to come up, hopefully not at 3 a.m. next week, but you know, that'll come up sometime when you're working on hash code. So I'm just putting that out there for now, but we're not going to worry about that. I'm going to leave that as a comment. The effect that we're after is we want to take the key and store it in hash table, whatever index we got to, the key piece, and store the value in the value piece. Okay, and then one more step. Set the valid equal to 1. So if my key was butter and my value was 2 sticks, I set the valid to 1. This is supposing index was equal to 2, right? So I'm making a hash of a chocolate chip cookie recipe. So so at the entry associated with the key butter, we store the value and we set the valid to 1. And now when we're looking at our hash table, we know, for example, that, you know, there's going to be something here and here, but if valid is 0, we don't consider those as part of the hash. But here we see valid equal to 1, so we know that's part of the table, and it's a valid key data pair. All right. So there's one other thing we have to do when we're putting into our table. Because if I try to put something else into our table and it comes up with a hash index of 2, if I just go ahead and I copy it into location 2, I'm going to wipe out what's already there. So we need to do what? Check for a collision. All right. So our hash function, I said we could have a better hash function that takes 2 arguments, a key and a probe number. And the probe number basically gives you a different hash value with each attempt that you make. So let's embellish this. Let's hash key comma 0. Where the 0 means first attempt. So we check for a collision. How do we check for a collision? We've hashed our key. We've got an index we're going to try to store. If the valid field is 1, cool. Okay, so if this is equal to 1, we've got a collision. And what should we do in that case? We should rehash with a probe value of 1. And if that gives us a collision, we should rehash with a probe value of 2. So let me call this a variable. So let's do like, and we'll write this up cleanly afterwards. Let's do this like probe equals 0. And we'll use that as our argument to our hash function. Okay, so while we have a collision, let's increment our probe value and change our index. All right. So probe is equal to 0. Index equals hash of our key with that first probe value. If that valid flag is 0, we don't do any of this. We just go on, we store our data and our key, and we set the valid flag. But if we have a collision, change the probe to 1, change your index to the new hash value, go back and check to see if that's got a collision. If it does, change the probe to 2, set your index to the hash value. When you try with probe value 2, go back, check for a collision. Does that make sense? All right, how can we get into trouble with this? It is complicated. So what goes wrong with this? We will need to clear the valid flags when we delete something, definitely. But even before that, just trying to put a piece of data in, what's the bad thing that could happen with this code? Not a sig fault, not uninitialized stuff. I mean, those are bad things, but that's not something that's going to come up in this. No memory leaks yet. We'll make some memory leaks later. Something right here. Infinite loop. What if there's no space left in the table? This will just keep trying again and again and again. Excellent. Or if our hash function is very poor, and on every probe attempt or every few probe attempts it comes back to the same set of locations to try. Now a good probe function would try, all 31 locations before retrying a location again. But either way, at some point, our table may be so full that we don't find a case where valid is not equal to 1. So we need a way to kick out of here. All right, so let's write this up now a little cleaner. This is still not quite C code. This is still pseudocode because I want to leave some fun for you. But let's put a key data pair into our table. Okay, so let's start with an attempt number. Let's hash our key with that number. And then let's check for collisions. So while the valid flag at that location is set, let's do let's increment our probe and rehash with that. And let's put a check in here. And if our probe attempt is bigger than our maximum number of tries, do something to say we're out of space. Otherwise, you know, go ahead, get a new index, see if that's available. When you come out of this loop, your index points to a spot where you have room to store your data, so so do your malloc and your string copy or whatever else so that you can copy your key into there. Copy the data. And set your valid flag. Alright, that pretty much does you. Alright, so saving in the hash, there's some work to do, but it's pretty straightforward, right? Find an index. If it's available, store it there. If not, find another index. See if you can store it there. If not, find another index. See if you can store it there. Eventually, you either find an open spot and you store your key data, set it as valid, or you decide that you're out of spots and you do whatever you're supposed to do when you're out of memory, out of space in your hash table. So your put could, you know, return a success value. So maybe if you're out of space, you just return 0. Otherwise, you return 1, or whatever you choose. All right. So that's saving in the hash, and then searching. Is straightforward, right? If you want to search for a key, take the key, hash it, see if there's something at that location where the valid flag is 1. But we have to do one other thing. So, okay, so it's not as straightforward. So let's do search. So let's start with 0. And we'll hash our key using that first probe attempt. All right, so if at that location in the hash table we find the valid flag set, what can we say at that point? We've hashed our key, we've gone to the table, we found that the valid flag is set. What do we know at this point? We know that something is there, exactly. But we don't know that it's our key. We know there's something in the table there. So something's here. But we don't know that it's our key because it's possible that when we tried to store our key, there was already something in the table there and our key got stored somewhere else. So we have to check. So if our key is equal to what's in the hash table at that location, then success, we found what we're looking for. if this is not the key that we're looking for, we're not ready to say the key's not in there, because it might have been stored at a different location. So what do? We rehash. And then we go back up here and we try again. If that location is invalid, then we know our key is not in the table. If that location is valid, then we check to see if it matches our key. And if it does, success. If not, we need to try again. And we keep doing this, but stop after some number of tries. At which point we say fail. So this business of rehashing is going to come up in all of these functions. And when we delete, it's going to make things even more interesting. All right, so we're out of time here. That's a good start on the actual algorithms for these. So we won't be actually implementing hash functions in C for a few more days. So we'll build this up. All right, so you're good to go. Let's see. Before you leave, real quick, I'm having trouble with the ODP. I'm getting the correct number for, but assess give me 0, 10 for all 3 tests. All right, I will take a look at that, but you're good to go, and I will see you next time. And I'm going to stop recording, but I'll hang out here.